Okay, this chapter is dealing with magnetic fields, right? So the previous chapter dealt with electrodynamics, motion of electrons. The one before that, electrostatics, stationary electrons. Now we're talking about magnetic fields. A magnetic field arises when an electron moves. When an electron moves, there's a motion of charge, but there's also the creation of a magnetic field. The magnetic field is the region of magnetic influence around a magnetic pole or a moving charged particle. All magnetism is created by moving charge. That is our current understanding. If you ever come across a situation where a magnetic field is created by something that's not a moving charge, you'll probably get a Nobel Prize, right? So you can see that I've already given you 3 Nobel Prize assignments in the course of this one lecture, right? So here's a horseshoe magnet, right? So it's called a horseshoe magnet because these are the shoes that horses wear when they want to fly, right? Isn't that what we said? You wear this and then you levitate? Okay, so here's a horseshoe. It looks like a horseshoe. North pole, south pole, and what happens is now you've got magnetic. This is a magnetic pole, magnetic north pole, magnetic south pole, and you've got these lines of field lines, except these are magnetic field lines, right? Now you can actually see them in a way by taking a magnet with a north pole here, south pole here, put a transparency over it, and sprinkle iron filings. And you'll find that the iron filings, they end up in this pattern where the filings are lining up along the magnetic field lines, similar to what we saw in a previous lecture dealing with electric charge. Now, if you have 2 magnets, you end up, so here's a magnet where it's north pole, south pole. Another magnet, apply the south pole and the north pole. So they're flipped. What happens is the field lines of one magnet interact with the field lines of the other magnet. So you can see there's a straight field line between the north pole here and the south pole here. And then here you got a strange pattern and you've got the field lines going from north to south like this, right? And each of these field lines is now a representation of the trajectory of a magnetic pole. With electric field lines, we said, if you're a positive charge and if you're a negative charge, and if I were to take a positive charge and place it near you, you would repel the positive charge and she would attract the positive charge and it would come to you. Right? That's what we described with the electric field lines. We're going to replace exactly the same situation now. You're a north pole, you're a south pole. If I were to take a north pole and place it here, magnetic pole, you would push this north pole away and it would move, thank you, extra credit, right? It would move along this trajectory until it came to you, who's the south pole. Right? The north pole likes the south pole and vice versa, right? So that's what these magnetic field lines are representing. Now, what happens is a magnet, remember that I said that if you were a north pole and if I were to bring a north pole next to you, you push it away, right? So same thing happens here. If you were to take a compass needle that has a north pole and a south pole and place it in a magnetic field, these are magnetic field lines, what happens is this north pole will interact with the magnetic field lines and experience a force pulling it in this direction. The south pole experiences a force from the field lines in that direction. So taken together, this creates a torque, right? Here's a force, and it'll rotate the needle, right? So this needle, experiencing these two forces, will rotate because it has a component that's perpendicular to the needle, will rotate about this fulcrum or about the pin until it lines up. So once it lines up, there is the force in that direction, in this direction, and there's no remaining torque. So, and this is how a compass needle works, right? Little compass, you walk around Earth's magnetic field, it lines up telling you where's north, right? That's the same principle here. Why exactly does this work? We don't know. So, introducing the concept of induced magnetism. Here's a student, there's a horseshoe magnet, and the magnet picks up an iron nail, right? Because of magnetism. Now what happens is, this horseshoe magnet induces a magnetic field in the first nail, which can then be used to pick up a second nail, which can then be used to pick up a third nail. So this is induced magnetism. The magnetism is induced in these additional nails. What's going on here? To help that, we look at this concept of magnetic domains. So this is a piece of iron, for instance, and what happens is these are single crystals. This is a crystal inside the iron, or it's called a domain. In the domain, all of the atoms are lined up one way. So we can look at this kind of like this. If I stand in front of you and if I look at the students, I notice that all of you are oriented in this direction, right? So you are a domain of students, all of you facing this way. Now, what happens is, while I stand here, if you look at the domain of students to the extreme right, notice that they're not facing straight ahead. Do you see that? They're facing in this, for some strange reason, I don't understand. They're facing in this direction, right? So notice what happens is, this domain of students are lined up this way, that domain of students are lined up this way, right? And that domain of students is kind of randomized, like pointing in random directions. Oh, no longer. They woke up. Right? So similarly, in this domain of students, all the students are pointing this way. In this domain of students, they're all pointing this way. In this domain of students, they're all pointing this way. Apply this to atoms, all the atoms pointing this way, that way, that way. Right? Now, in some materials like iron, what happens is, each atom can be viewed as having a magnetic north pole and a south pole. So, if all the iron atoms are pointed so that the north pole is pointing this way, this domain ends up with a north pole here and a south pole here. This domain ends up with a north pole here and a south pole here. It kind of cancels each other out. So on average, all these different domains, the north and south poles in iron, will cancel out. So iron by itself tends to not be magnetic. However, if I were to take this material and align all of the atoms by putting the iron in a very strong magnetic field and heating it and then cooling it, what will happen is, instead of being randomized, pointing in random directions like unmagnetized iron, if you slightly magnetize it, they will tend to point in the same direction. If I strongly magnetize the iron, they all line up in the same direction. So now you see a very strong magnetic north pole here. You have a weak magnetic north pole here and no north pole over there, right? Now if I break this in two, what happens is, because of the directional pointing, if you will, of the atoms, you end up with a north pole here, south pole. And this second piece has a south pole and a north pole. Now, on the right here is an application of magnetic fields. You've probably heard of maglev trains, right? Magnetic levitated trains. So Japan famously had the first one, whatever. They can travel really fast. And it's also sometimes called the bullet train, because the front of the train looks like a bullet to minimize air resistance. Basically what happens, the reason why a maglev train is able to travel so fast is the normal trains, you know what happens. They have got these metal wheels that sit on metal tracks, right? So the wheel is sitting on the track, and as the train moves, there's friction between the wheel and the track, there's friction with the axles and so on. And so that slows the train down. Now, in a maglev train, what happens is, you apply a magnetic field and you levitate the train. So the train lifts up off of the tracks. So it's actually floating above the tracks, there's no contact. Now, you apply a magnetic field force that causes the train to move forward. And so you can travel really fast because there's no friction with the tracks at all, right? So that's the principle behind maglev trains. And there are different kinds of applications of this. So this is an example of technology. Mademoiselle?
When it stops, does it then sit, or is it always just hovering?
You can do it either way. When it comes to the station, you could have you'll have electromagnets and permanent magnets typically, or electromagnets and electromagnets, and you could have the power off and have it power on and have it stand up. If you're just stationary, just coming to stop at a station for 3 minutes, leave them on. But if you come and stop and you're going to be overnight off of the train and it's just going to be sitting there, you can switch it all off and right, and have it, and then it would sink down onto the tracks. Extra credit for the question. Okay, so I said that magnetic fields are created by moving charge. So what happens is, if you have a wire like at the very top and a current is traveling in the wire, it creates magnetic field lines. So let's say this is the wire, the current is traveling in this direction. As it's traveling in this direction, it creates field lines like my fingers, curved around. Right? So field lines, magnetic field lines, they curve around this wire where the current is traveling in this direction. Right? So any wire that has current traveling in it will have magnetic field lines that spiral around. So what happens now? If you take that single wire and make it into a loop, if you make it into a loop like this, a single loop, you end up with the field lines all coming into the loop in the center and coming out of the loop on the outside. So you can concentrate the magnetic field lines by doing that. Now you can actually plot, if you will, the magnetic field lines by doing this. So here is a wire, there's a piece of paper with a wire going down through the paper, send a current through this, now sprinkle iron filings, and the iron filings arrange themselves in these circles that represent the field lines, right, for a current traveling now in this direction. Now you take this wire and make a loop like this, send current up into this wire through here and down, and now you sprinkle the iron filings, and what happens is you get the rings like this and concentrated field lines. Now if you take these wire loops and you make it into a spiral, right, now what happens is all the field lines collect in here in the middle, and what you have just created is an electromagnet. All you do is take a wire, coil of wire, wrap it around, and the field lines concentrate in the center, and what happens is this wire with the current traveling through it behaves as if this is a north pole and that's a south pole. So that's where the idea of an electromagnet comes from.
So with the wire, the current isn't actually going along the wire, it's going around it.
The electric current is traveling through the wire.
It is.
Yes. So here's the wire. Electric current is just traveling, let's say, from here to here. When the electric current, which is the flow of electrons, is traveling in this direction, it creates a magnetic field. That's what is going around. Magnetic field lines are going around. Not the current. Current is traveling in this direction. It's creating magnetic field lines going around. Yes, sir?
I thought that electrons traveled on the surface like a copper wire. You have one copper wire, and electrons run down the surface of that. Let's say you have a bundle of copper wires. That's going to conduct more electricity than a solid copper wire of the same diameter.
Okay. Beyond the scope of this class, but to a first approximation, what you're referring to is called the skin effect.
Okay.
So what are you talking about?
I think so.
Yes.
Okay.
The skin effect is related to the frequency of the, beyond the scope of this class, right? But it's related to the frequency of the oscillation of the electrons.
Okay.
So in a wire, the higher the frequency, the more to the surface the current travels.
Okay.
But as the frequency drops, the flow of electrons spreads throughout the bulk of the wire. Right? So at very, very low frequencies, to a first approximation, you can think of the current as uniform through the wire.
Right.
Right. Right. But higher frequency, as the frequency goes up, it moves more and more towards the skin, right? Towards the edge. Extra credit for the question. Okay, so that's the electromagnet. So, introducing the concept of a magnetic force. A magnetic force between two magnets. Yeah, all of these slides are available on the website. So you can just print them out, right? Just print. You can always write down the slide number if it's available, and then make a note. And I'll tell you what slide number. It's 24.6. Right? So between two magnets, the magnetic force is the attraction of unlike poles, magnetic poles for each other, and the repulsion of like poles. Which means here's the north pole, here's the south pole. They attract. Here's the north pole, here's the north pole. They repel. This is the magnetic force. Magnetic force can also arise between a magnetic field and a moving charged particle. So if there's a magnetic field in this room, let's say that the magnetic field lines are traveling like this, and if I have an electron traveling in this direction, I experience a force that uses the right hand rule, which is it is the perpendicular between the magnetic field line and my motion as an electron. Right? So the magnetic field line is like this. I'm sending a current, let's say, in this direction, and what will happen is the field will be perpendicular to both of these directions. So this direction, right hand rule will be a force like this in the third dimension compared to these two, right? So that is what the second part of the magnetic force is talking about. So here's an illustration of this. If you have a horseshoe magnet, you have an electron beam, that's just a beam of electrons traveling in a straight line. What happens is as soon as it interacts with the magnetic field, it's deflected. The force is perpendicular. Field lines go from north to south, straight line like this. Electron beam traveling in a straight line like this. So this is the x-axis, that's the y-axis. The force is along the z-axis, perpendicular to the x and the y, right? And you can actually see this where if you were to take a wire and put it straight between the legs, the arms, whatever of this magnet, send a current through it, all of a sudden the wire that's like it's straight when it's just sitting here, send a current, it'll just bow, right? It'll, in this case, current traveling this direction, it bows upwards, current traveling the opposite direction, it bows downwards. And you can actually apply this in an instrument called a galvanometer, where you have a coil of wire, you send a current through it, and the current generates a magnetic field. A compass needle interacts with the magnetic field and lines up, right? If you have a spring that's pushing against that motion, you can end up with a pointer that points more or less depending on the strength of the current. So that becomes a voltmeter. Higher voltage, higher current, and you dial this up lower voltage, lower current, and you dial this down, right? So that's the principle behind voltmeters and ammeters and so on. So traditionally, even in cars, it used to be that you have got these different gauges. Ultimately, they'd use some principle like this. Yes, sir.
So what does that do to AC with the copper wire? The AC doesn't flip them back and forth?
Yes. In the case of an AC that's going through this, the wire will actually oscillate up and down, depending on the frequency. The wire has a certain frequency up to which it can respond. So if the frequency is low enough for the wire to be able to respond, you will actually see the wire doing this. So you can get it to dance, right?
So that basically takes its wave, sine wave.
That would be, if you look at the peak amp, if you look at the center of the wire, it would trace out a sine wave. Good point, extra credit, right? Okay, today is Wednesday, so go forth, have a good weekend. And don't forget that the test is on Monday, right? Test coming up Monday. Don't forget to study.